So let's create a short video today explaining how edge detections work in image processing. The basic idea is how can we detect an edge. So first we want to look at the image on the bottom. Like imagine this is like an image, like a very simple one. Like the width is 20 pixels and the height is 1 pixels. We can see that the image is actually slowly changing from blacks to white color, and above that we can plot like the image intensities, where it will help us to visualize how it actually changed the value. So to detect an edge, like for example, we can draw many lines to separate the black and white. And if we look at here, we have one edge right here, but it's possible to have other edge as well. So how can we know which one is the best one? So by calculating the first derivative of the intensity functions, we can see that for example, this point right here on the first derivative, like is slowly changing from black to white. But right here, we're gonna write an edge right here, and when it reaches the top, we say that at this point it has the highest gradient, and from that we just need to write our edge right here, and it will separate the black to the white nicely. What if we want to process the color image? We have this image right here, and it's actually made up of 3 channels: red, green and blue. So in here we only see the combinations of the 3 channels, but actually 3 images stacked on top of them. For example, when we look at these pixels right here, it's gonna be a combination of the red and the green and the blue, and when we combine them together, we will have this pixel over here. So the idea is when we want to detect the edge of an image, we cannot use those 3 channels color, so we want to combine them together. So we use the value of red and we put into here, value of green we put into here, blue into here, because each image it has different intensity. So the red and the green and the blue, so we want to give them different weight, and now you multiply them together and you will have the actual value representing the intensities of the image on the left. But the problem with this is it's continuous. So when it is continuous functions, we will be able to use some gradient functions to calculate the highest gradient. For processing an image, like it's not that straightforward, because this value right here is not continuous. So what we want to do is we can approximate the values by using the 3 point, previous point, current point and the next point, and we can approximate the values of them. There are 2 common finite differences we can use. The first one is the forward difference. The next one is the backward difference. For example, we want to measure the change of this current point x right here. So what we want to do is we use this function, and we can use the next point, which is this one, combining them with the current point. Basic idea is we're using the current point and the next point to calculate the derivative. Another ways to use it is we can use the previous point, which is right here, and with the current point that we are estimating, which is right here, and we can calculate the actual change in that direction. Here's an example of when we use the gradients on top of this value. So we have the x derivative. Let's call this is the width of the image, representing the width dimension, and in here is the height of the image. Now for example, we want to measure the gradient of these points right here. So first we need to transform them into raw pixels value. We have the 247, 248, and if we look at these values right here, it's going to be 18. We want to use the neighbor points that very close to our point. For example, we have the 10, 20, 255, 210, 254, which are the values on the x directions, which is the neighbors of our points that we are assessing. So from that, we have this one. And even though that I mentioned that we have two types of finite difference, but in image processing, it makes more sense to use the points on the right and the points on the left as well. That type of finite difference is we call it central difference, where we calculate the next value with the previous value. For example, this is the point that we are assessing, and we want to get the next value, so it's going to be this one. So we just plug that into here, then we subtract by the previous point, which is right here, and then we divide it by the 2, and we get this value. 100 is the gradient of the red point by using the neighbor's value. Because we're using the central difference, we have a filter that we can actually apply to the image, and you can see that we are using the next value, and we're using the previous value as our x derivative. It's gonna be the same case for the y derivative, but now instead of doing x directions, we're gonna do it in the y directions. So here's the points that we are assessing, number 18. We just need to measure it with the neighbors. So 245, 254, 153, and 105. We also apply the central difference, and that will result in the y derivative right here. We can apply that filter, and we gonna like move them like a sliding windows from left to right by using the convolutions operations. We have the filter, the yellow filter on the left, and after we apply the convolutions, we will see that we know the gradient of each pixel. For example, you can see the gradient of these pixels right here, and the combinations of those pixels allow us to draw an edge that like distinguish the bicycle from the rest of the image. So we're just following the gradient. There are actually a lot of algorithms to work on this one. The idea is based on this gradient. There's a lot of things we can do with them. To have a look at how the convolution operations work, let's look at a 5 to 5 image. We can see that we are applying the filter, and the receptive field is like a sliding window, and it slides through all the values in that our input image. And now we will have the gradient of our image, and here is using a pre-width filter. There's one thing that you will notice is that the size after we apply is gonna change into a smaller one. So the way we want to avoid this is to add some padding, like some values right here around this, and when you run it, so now the size is not 5 and 5, it's 7 and 7. So after you apply that, the feature map will become 5 to 5, which is equal to the original image. Basically from that, we will have the gradient of each of the pixels. Basically, we have the x derivative like right in here, but if you look closely, like the filter is not very collapsed, but it is a trees to trees filter in this case. So the reason we want to do that is we can look at more values at once. For example, this is our x value. We can look at this value right here, look at this value right here. We can look at all directions. and we can calculate the gradients based on those directions as well. If your filter is small like this one, like it can only look to the left or to the right, but we want our receptive field to be bigger, and like it can process and understand more information, so we use this filter instead of this one. And the way we do that is we combine them with another vector, so we call them the weighted average. So for examples, we have number 1, 2 and 1, so we get back to these values later. The idea is based on these factors right here, combining them with the x derivative, we can have our filter, which is 3 by 3. After you multiply them through the dot products together, you will have the Sobel filter, which is a very famous one in image processing. Based on these filters right here, we can also scale it as well. For example, we have 1 to 1, so we just scale that with an s value, so we just multiply them together, and you can see is that the value is actually changed into s value, so we call that scaling. Let's talk about the number 2 again. So the number 2 in the Sobel, it actually reflects the center rows in the Sobel, so it is saying that this value, like number 2 minus 2, is more important than the rest of these values right here. So what I mean by that, if we look at these examples right here, we have a value because we have this is 2, this is 2, this is 2. So it means that these values, when it multiplies with our current the pixels, it will have more impact on the gradients right here. And the values like 1, 1 and 1, when you multiply that, it's not gonna give as much weight or importance to gradients. It's gonna be based on different types of operators. If you look at the pre-width operators right here, it will treat every values the same, like it's not number 2s like the Sobel. So if we go back into here, everything is 1, so it will treat the left neighbor, right neighbor, up neighbor and down neighbor, it will treat them the same. Based on that, it will have different results on the gradient. Based on the size and the scales and the weight, we can have different types of gradient based operator. Like even the scar, the weight is different, and rubber size, it's just gonna be 2 by 2. Another thing that you will notice is that the left and the right is now a little bit changed, because now it is positive and this is negative. But in our last example, like right in here, we can see that this is actually negative and this is positive. So it doesn't matter, as long as the two sides of the opposite values have the opposite value, then it is good for indicating the directions of the gradient.